let us see the concept of pole and polar. This pole and polar, if you see the definition is the locus of point of intersection of the tangents, the locus of point of intersection of tangents. Like what? Let us take this is the point and the locus. That is locus of point of intersection of tangent. These two must be tangents. Now, tangents to what? Any curve, maybe circle, parabola, ellipse, hyperbola, whatever it is. So let us take the circle now. The locus of point of intersection of tangents. Drawn to any curve. Here I have taken a circle. Drawn to any curve. In this case, circle taken. How the tangents are and where they are drawn. Drawn at the extremities of the card. This is a card. Drawn at the extremities of the card. So, how the card is? This card is passing through a fixed point. I repeat, the locus of point of intersection. This is the point of the locus. The locus of point of intersection of the tangents. Where the tangents are drawn at the extremities of the cards. How the cards are? Passing through a fixed point. Let me say the fixed point as P. Passing through the fixed point P. Always forms a straight line which is called the polar, and the fixed point is called the pole. Let us enlarge it. Like what? I have taken one card here. No? Let me take another card passing through the same point P. Like this. This is another card. Can be drawn like this. Another card can be drawn like this. So here this card is intersecting the circle. Obviously the card now it has 2 points of intersection on the circle. Now if you draw the tangent at this point of intersection and if you draw the tangent at this point of intersection, they are intersecting at this point. You understand? Huh? So, this is another card, and at the extremities of the card, 2 more tangents are drawn, they are intersecting at this point. Similarly, you can take one more card like this. This is another card. Now, at the extremities of this card also, you can draw one tangent like this, and another tangent like this. So, this is also intersecting at a point. So, now if you see the definition, it will be now clear for you. If you see the definition, the locus of point of intersection, these are the points on the locus. The locus of point of intersection of what? Of tangents. How the tangents are, and where they are drawn at the extremities of these cards. How these cards are? Passing through a fixed point P. Always forms a straight line. The straight line is known to be the polar, and the fixed point is known to be the pole. This is the definition of pole and polar. Let me repeat this. Let me repeat this. The locus of point of intersection of what? Point of intersection of tangents. Tangents. How the tangents are, where they are drawn. Tangents that are drawn at the extremities of the cards. That are drawn at the extremities of the cards. How these cards are passing through a fixed point. Passing through a fixed point always forms a straight line. Which forms a straight line? The locus. The locus forms a straight line, and the straight line is known to be the polar. That is, the locus is said to be the polar, and the fixed point is said to be the pole. This is what the definition of pole and polar. So the locus of point of intersection of tangents drawn at the extremities of the cards, passing through a fixed point, always forms a straight line called polar, and the fixed point is called pole. This is what the definition of pole and polar. Now let us write the equation of the polar. Let us write the equation of the polar. So it's very simple. Equation of polar is like this. Equation of the polar. How do we find out? Generally, while finding the equation to the locus, while we always take by taking the point on the locus as p x naught y naught. Let us take p x naught y naught as a point on the locus. Let us take p x naught y naught as a point on the locus, and the fixed point as some q x1 y. The fixed point as q some x1 y. Let us take the equation of the circle as x square plus y square minus r square equal to 0. Okay. Now, what is our interest here? What is our interest here? We want to understand the equation to the polar of q. We want to understand the equation to the polar of q with respect to the circle s is equal to 0. With respect to the circle s is equal to 0. So, let us start now. Let us start now. Now, through q, draw a card. Through q, draw a card. We have drawn a card here. This card is intersecting in 2 points. This card is intersecting in 2 points. Now, if you draw the tangents at the extremities of these cards, that will intersect at a point. That will intersect at a point. Let me take this point as p x naught y naught because I need the equation to the locus of p only. I need the equation to the locus of p only. So, now, how do we start with now? Let us take the card of contact of P with respect to S equal to 0. What is the meaning of card of contact? If you draw tangents from P to the circle, they touch the circle in 2 points, and the line joining these two is nothing but the card of contact. So, what is card of contact for this? Card of contact is S1 equal to 0. That is x naught plus y naught minus r square equal to 0 is the equation to the card of contact. But how this card will be? It always passes through a fixed point. What is the fixed point here? x1, y1. Therefore, this q must satisfy this equation. But it passes through q x1 y. Therefore, x1 x naught plus y1 y naught minus r square equal to 0, and hence the locus of P, which is nothing but the straight line, is given by x1 x plus y1 y minus r square equal to 0, because you know the point of the locus is x naught y naught. Finally, it is to be converted as xy. That means we are generalizing the equation. The generalized equation is xx1 plus y1 minus r square equal to 0, which is also s1 equal to 0. So, what is the equation to the locus. What is the equation to the locus of point P, which is nothing but the polar, is nothing but S1 equal to 0 with respect to this curve S equal to 0. So you remember the formula will be one and the same. The formula will be one and the same for every curve. What I mean to say here, if you are given a point, let me say, if you are given a point to find pole, of a given line, to find pole of a given line with respect to a given curve. With respect to a given curve, I have taken a simple curve here. You can have any curve of any size. The method is one and the same. Any curve of any size, the method is one and the same. Let me say the curve as s is equal to x square plus y square minus r square equal to 0. And the polar is Lx plus my plus n equal to 0. And polar is Lx plus my plus n equal to 0. Now, what is our interest here? We want to find out the pole of this line Lx plus my plus n equal to 0. What is the method? Method is uniform throughout. Remember that. So, let Px1, y1 be the pole. Therefore, polar is, according to the formula here, S1 equal to 0, we have just now derived. Polar is xx1 plus yy1 minus r square equal to 0 is the polar we have got by considering the pole as x1, y1. But the polar is already given in equation 1. And this is equation 2, which we have got. 1 and 2 are same. Compare these two. X1 by L is equal to y1 by m is equal to minus r square by n. Okay, now what is that you get from this one? Pole as x1 y1 is nothing but cross multiply this minus lr square by n comma minus mr square by n. This is the formula to find out the pole of a given line Lx plus my plus n equal to 0 with a simple circle x square plus y square minus r square equal to 0. What I mean to say by simple circle, it is given in the simplest form. If it is given in the full form also, the method is one and the same. What is the method? Start by taking the pole as x1, y1. Write the polar equation S1 equal to 0 using this. Just now we derived it. And we have got our polar now in terms of x1, y1. But the polar is already given Lx plus my plus n equal to 0. Let it be 1, let it be 2. Now 1 and 2 represents the same. We compare them to get the point x1, y1, which is nothing but the pole of the line Lx plus my plus n equal to 0 with respect to the circle x square plus y square minus r square equal to 0. Now, what extra things you have to remember with regards to pole and polar is that if the point is pole is lying outside, the polar intersects the circle. If the pole is lying outside the circle or the curve, the polar intersects the curve. And if the pole is lying inside the circle, then what happens? The cards, it will be like this. Then the polar will be lying outside the circle. Or polar will never intersect the circle. It lies outside the circle. So if the point P or pole lies inside the curve, the polar never intersects the curve. If the pole lies outside the curve, then the polar intersects the curve. If the pole lies on the curve, if the pole lies on the curve, let us see what happens here. Let us see what happens here. If this is a circle, let me say, and this is the pole, let me say. Now through this pole, the cards will be passing through like this. Then what happens? This is one tangent drawn at the P. And you can draw only one tangent there because the point is lying on the curve now. Now if you draw another tangent here, it intersects here. If you draw another tangent here, it intersects here. If you draw another tangent, it intersects here. These are the points on the locus, understand. These are the points on the locus. So this polar is nothing but the tangent. This polar is nothing but the tangent. So what is your what should be your broad understanding about the polar? If the point or the pole lies outside the curve, the polar intersects the curve. If the point P or the pole lies inside the curve, the polar never intersects the curve. Never intersects the curve. If the point lies on the curve, the polar itself is the tangent. So we can see like this now. It is nothing but the polar tangent. Let us think like that. It is nothing but the polar tangent. It is nothing but the polar card. This is nothing but the polar card. But in this case, it is polar only. There is no other name for it. There is no other name for it. So you can understand that the polar can be taken in three different forms. In this case, it is polar tangent. In this case, it is polar tangent. In this case, it is polar card. In this case, the polar is polar only. Polar only. Now, with regards to some other properties of pole and polar, there are conjugate points and conjugate lines. Let us see what are they. Let us see what are they. Conjugate points. Conjugate points means it is very simple. It is very simple. Conjugate points. And let me explain here itself, and lines also. What are the conjugate points? 2 points are said to be conjugate. 2 points are said to be conjugate if 2 points are said to be conjugate if the polar of either passes through the other. 2 points are said to be conjugate if the polar of either passes through the other. What does it mean? For example, you have, let us change the curve. Let us change the curve. For example, I am taking a parabola now. Because I want to make you understand that the concept is uniform throughout except the equation of the curve. Here in this case, I am taking up the parabola in the standard form as y square is equal to 4ax. As y square equal to 4ax. Now, let me take a point P here as x1, y. And obviously, you know, the polar never intersect the curve because the pole is lying inside the curve now, So if you take the polar, let us suppose the polar is like this. This is the polar of what? P. Polar of P. Now, there is another point Q. There is another point Q. It is in this way. It is like this. The Q, let us suppose it is lying here. Let it be some x2, y2. Then if you draw the polar of this, that polar passes through. For example, this is a card passing through this. This is the card passing through this. Then what happens? The tangent is drawn at the extremities of this, or like this. The tangent is drawn at the extremities of this is like this. then this polar passes through P, understand that. What is this? This is polar of Q. So now you'll clearly understand that 2 points P and Q, this is x2, y2, this is x2, y2. Two points P and Q are said to be conjugate points if the polar of P passes through Q, and as well the polar of Q passes through P. This is what the conjugate points are. So simply you can say like this: 2 points P and Q are said to be conjugate points with respect to a curve s equal to 0. With respect to a curve s equal to 0, if the polar of either passes through the other. If the polar of either passes through the other. For this one, very simple, polar of P is y1 minus 2a into x plus x1 equal to 0. But Q lies on it. Q lies on it. Therefore, y1, y2 minus 2a into x1 plus x2 equal to 0. So the condition for conjugate points, the condition for conjugate points is S12 equal to 0. Remember that. Condition for conjugate points is S12 equal to 0. So with respect to points, lines will be there. Obviously, with respect to lines, points will be there. What I mean to say here, points means poles will be there. So you can simply understand the definition of conjugate lines now. What are the conjugate lines? Two lines are said to be conjugate. Two lines are said to be conjugate if the pole of either lies on the other. Because it is a line passes through. Because it is a line passes through the other point. But there, the lines, for lines you will have poles. So two lines are said to be conjugate if the pole of either lies on the other. For example, you have two lines here, L1x plus M1y plus N1 equal to 0, L2x plus M2y plus N2 equal to 0 be the conjugate lines. We are now deriving the condition for these two lines to be conjugate with respect to what? S equal to 0, the parabola. S equal to 0, the parabola. Now, let us write the pole of this first line. After writing the pole of the first line, if they are conjugate lines, that pole must lie on this. So, we are now applying the procedure what we have learned. How to find the pole of this. Let the pole be. We don't know the pole. Let the pole be what? P, x1, y1. Then what is a polar? Polar, S1 equal to 0. S1 equal to 0 for this. That is y1 minus 2a into x plus x1 equal to 0. This is the polar we have got. But the polar is already given. This is 1. This is 2. 1 and 2 are same. Come on, compare it now. This is y1 divided by y coefficient here, m1. This is minus 2a. X coefficient here, L1. Constant here, minus 2a x1. And constant here, n1. From this one, you will be getting the x1 comma y1, which is nothing but the pole of this line. What is the pole of this line now? Write x1 from this one. It is n1 by L1, comma, y1 please, minus 2a m1 by L. This is a pole of the first line. If they are conjugate lines, this pole must lie on the second line. Let us substitute that here. Now, this is Substitute this please. In the second equation, L2 into N1 by L1 plus this one, M2 into this one, minus 2A M1 by L1 plus N2 equal to 0, implies L1 N2, after rearranging this, L1 N2 plus L2 N1 is equal to 2A M1 M2 is the condition for conjugate lines. So, how do we conclude it now? 2 points are said to be conjugate points with respect to a curve s equal to 0. If the polar of either passes through the other. If the polar of either passes through the other and the condition is s12 equal to 0. Two lines are said to be conjugate lines if the pole of either lies on the other. Condition for conjugate lines is S12 equal to 0, and the condition for conjugate condition for conjugate points is S12 equal to 0, and condition for conjugate lines is L1 and 2 plus L2 and 1 is equal to 2A and 1 and 2. Remember, this is not a universal condition because we have taken the parabola in the simplest form, y square equal to 4x. Remember the method please. That will be comfortable to apply to any curve, like what I mean to say here, whatever the size of the curve it is, to find out the pole, what is the method to be followed, just remember this. Step number 1, let the pole be x1, y. Step number 2, write the polar with respect to the given curve. This polar is nothing but our polar in terms of x1, y. But the polar is already given in the question. Now, this is the polar we have got. This is the polar given. These two must be one and the same. By comparing these two, you will get the pole of the given line. That is a method, if you understand. That will be universal method, and you need not have to remember any formula. If you remember the method. Similarly, how to find the condition for the conjugate lines. Two lines will be given. If they are conjugate, find the pole of the first line using the method what I taught you just now, and substitute that pole in the second line because they are conjugate lines. The pole of this line must satisfy this line, and thereby you will get the condition for conjugate lines. If you apply the same in the problems, you will be more comfortable because you might be getting confused with many number of